So I'd like to invite back any speakers from our previous sessions. And also, I think we've got a few new faces that have agreed to join this panel discussion. So we will just spotlight, I think, the people we have. So I don't know, Catherine or Mike, if you're still around to join us. I think Oliver Brock, you may be available to join us, and a few others. And then we can have, brilliant, Catherine, thank you very much for joining. And then, yes, so I think we'll continue to, Oliver, I see, has joined us. Yes, so thank you very much for joining us after that talk. I just wonder, for me, Catherine, Oliver, do you have any reflections on Daniel's talk in terms of how this contextual awareness fits into what you're doing, into tactile sensing, into embodied research, perhaps from a more robotics perspective?
I mean, I'll just react very quickly. It's a lot to process, but it was really, really impressive. I'm not an expert on motor control, but we're always doing experiments with people who come in and try this. And because people vary so much, we switch them from this condition to this condition. And it just like terrified me that we're contaminating all of our data and people are context switching. And I need to read your paper and like really think. But thank you so much for explaining it. It made so much logical sense as you told the story. Oliver or Pumi?
Yes. So yeah, thank you, Daniel. This was always amazing introductory talk about your research, and I learned lots of things, but at the same time we're confused a lot, right? So this morning we had a Kenji Doya talk about the reinforcement learning, how we should understand our behaviors in the context of reinforcement learning. Then now you're introducing a lot of additional things, maybe on top of it or in the background of reinforcement learning. And also you talk about many different types of motor learning, like a strategy learning, skill learning, variability reduction, sequence learning. I'm sufficiently confused now. So if you can give us a bit of guidance, how we should think about all this variation of what we know about motor learning in humans, or we still don't know yet. What's your general impression about where we are?
So I think so. Reinforcement learning is not a threat to the coin model. I think you could have a coin model which had reinforcement learning. So people have done context-dependent reinforcement learning, where you transition between different reward payouts, and you have to realize you're in different things. So I think that's not a problem. I think our model could, instead of being an error base, we could think about it as reinforcement learning. I think the thing which I've left out of the coin model is trajectory generation. Like, I'm just assuming you get one number and you put one number out. Clearly that's ridiculous, but that's not a problem. The assumption is once you've done the estimation of what the force field is, then something else does that. And we think about optimal feedback control as a nice way of thinking about that. There's a nice biological thing where you have to have some cost function of energy and noise, and you think about signal dependent noise until you generate that. So that basically gets tacked together with this model. Strategy learning is a little bit harder for us. So we need a high level, like, what are the steps to tie a shoelace? That's beyond all this. That's more complicated, and we don't quite make it there, I would say, in these sorts of models. We're still working at a rather simple level. Noise reduction, I think, is part of optimal feedback control. You want to generate the trajectory in such a way that the noise doesn't cause problems. So I think they do all sort of fit together in the end. But we in our field tend to, when you and robotics have to deal with it all at once, we tend to slice off small parts which we can deal with tractably and ignore the rest in experiments.
Catherine.
Yeah, I wanted to ask Daniel actually a question. This is such a unique opportunity. Thank you for your beautiful talk. But a trend I've seen over the course of my career, as we do a lot of experiments with human participants, and not from a motor control, but like testing different technologies, or how this, I'm going to add haptic feedback and I'm going to take it away. Like when I started as a grad student, the popular wisdom was to do within subjects experiments where each participant tests all the conditions in randomized order and counterbalanced. But then each condition is a different context, and they're having to recognize that they're in a different context and adapt and try to mesh. And now what we do more is between subjects. So each participant, they only experience the system in one mode. And this has become more important when we do like Huggybot research or social agent, because I don't want to see the robot in it's a good hugging or not a good hugging, although we actually have done experiments like that. And I just wanted to ask, your recommendation would be, like between participant studies would probably give cleaner, because I'm only interacting with the system in this one context. We don't have to worry about these dynamics inside the person guessing and adapting. You agree, or did I misunderstand?
No, it depends. I mean, so it's true. We've now got an extra problem, if we believe the Coin model, that, you know, what a subject comes into an experiment with is going to totally affect how they perform. And you know, what number one thing to say is humans are incredibly variable at motor learning. You bring them into the lab, they're all different how they perform. Some learn really quickly, some go slowly, and some jump down, and there are all these weird things happening. And that's not surprising if everyone's got different experiences and they come with all these memories, which they're going to mix in different ways to try and learn your thing. We don't think of that. We think they come naive, like an empty brain, and then they learn our task. And that's just ridiculous. So in terms of the within subject between, I think that's really hard. So some experiments, I mean, what we do is we do within, and then we throw away all the data if it's just contaminated by what they did first.
We do that sometimes. We use only the first trial because we're like, now we know what was happening.
You know, but for some experiments, within is so much more powerful because of the variability between subjects. So there's no right answer, but you have a way of analyzing it to say, is everything I've done after this contaminated? Is what you see on the first block so different from what you see in that block for all the other subjects who did something first, that you do have an inbuilt control into that.
Really cool.
But it's hard. Yeah. We have problems with it. Sorry.
No, please.
No, I had nothing to say. Thank you.
I was just one topic that came up earlier was this idea of a Turing test, or how do we know if we've developed robots that have this embodied intelligence? I just wonder, again, on this discussion of human versus robot experiments, is a physical Turing test, we talked about it in the context of plants earlier, could that be an interesting way to actually assess learning, assess embodiment? Is that a nice benchmark for us to aim for as roboticists? Sorry, but both aimed at both the robotics camp and also the contextual inference camp to see if there's a difference of opinion there.
What would the Turing test be for motor learning?
That's my question.
That is a very good question.
I mean, they did run one. They ran the handshaking thing.
Yes.
Yeah. So that was the only one I remember. I thought it was a little bit ridiculous, but I mean, but people liked it. You know, could you tell it was a robot controlling, controlling itself versus the human controlling the robot effectively?
No, I think in Catherine's example, again, could you tell it's a robot or a human hugging? You need both. You need the sensory information, you need the motor control, you need contextual awareness of, do they want to be hugged, do they not? It's a nice combination of coming up with tasks that need all these elements together.
I'll quickly tell you, our robot would never fool anyone into thinking it's a human. Like in the final experiment that in Alexis's thesis, we hired an actress who played Huggybot. She dressed the same, she spoke and acted and moved. So we tried to control as much to make the robot and the person the same in there. But there was still, as soon as you see her, you immediately recognize and you hold her and touch her. But there were interesting differences. We weren't trying to pass the Turing test, and I would say I don't want to. The most surprising thing was that people actually preferred hugging the robot because they didn't have to worry about the social pressure of this person, and they were wasting her time and hugging her, and she could hear them breathing, and they could hug the robot longer and feel more comfortable of doing that because they knew it wasn't a person. It was just a dumb robot, but they could still gain comfort from it. So maybe we don't want to pass the Turing test. Oliver, do you have any robots that could pass a Turing test of any kind?
No, and I think the various Turing tests that have been proposed in the past sort of share many problems with benchmarks in general, right? That it's very difficult to separate a special purpose machine that does one thing, namely pass that Turing test, from something that we're really after, right? And so the only Turing test is survival, evolve and live. And that's obviously very difficult to do. But I want to take the opportunity that I'm speaking now to go back to a question that Lukas von Laake asked earlier, because I think this has been something that in the chat, this is something that is really worrying me a lot, and I'm thinking about it a lot. So I think it would be very interesting, Daniel, to get your input on this. The question which was rephrased from Professor Doya earlier this morning: can we infer internal mechanisms from observing behavior? And it's a kind of a benign question, but the more I think about it, the more impossible it seems, because all the models that we have are essentially Turing complete, which means that they can represent any function that is computable according to computational theory. And so basically, it means that any data you have can be fit by any model. And now you can start using Occam's razor and things like that, right? To try to, but Occam's razor according to what? What is simple? Something that appears simple to me is probably very different from what seems simple to a neural substrate. And so, I'm the director of a large research center that is basically hinging on that question, that we can observe behavior to infer mechanisms of intelligence. And so I really worry, and I'm asking the question, but I still think it's possible, and we can discuss this. But I wanted to hear what you think. How hopeless, and what do we have to do? How hopeless is it to actually, from the infinite space of possible models, find one that actually plausibly generates the data?
So I would say just observing behavior but not controlling the task, you can't learn very much. I mean, I showed you 3 examples of learning curves, which if you just observe them, you would have no idea what was going on under the hood in our very simple model. But I think the critical thing is to make predictions under new scenarios, as we did in that. We said a vote recovery. So we fit the spontaneous, we say, okay, if we do this, this should happen in this model, and then test it. So to me, that's stronger evidence that we're getting the underlying mechanisms right. So throughout my talk, we never measured those states, those predicted properties. They're all inferred by the model to fit just the motor output. So you could argue, yes, there are infinite many other models which could maybe do it, but this is a parsimonious one, which not only can explain those data sets and make predictions, but it can explain 15 data sets. And to me, that becomes powerful. Now, it's going to fail at some data sets. We will find data sets that fails at, and then we'll have to modify it.
Yeah. So, I mean, first of all, I didn't mean to attack what you presented in your presentation at all. And I totally agree with you, right? That if you don't predict anything, then you've done nothing. It's about prediction. But even the predictions that we usually do are very much within the vicinity of the behavior that we built a model for. And so I would suspect that out of the infinite number of models that explain the data, most of them, due to the fact that we don't have models, that we prefer models that are relatively simple, will generalize to the close vicinity of the data that we have used to create the model. So of course, I mean, the basic tenets of science still exist. We create models and we use them to make predictions. But still, I mean, the more complicated the behavior becomes that we want to predict, the more complicated the models become. We're hitting a combinatorial explosion where ultimately we won't be able to really get enough data to rule out competing models, right? And so, I don't have an answer. I'm working on one, and I have thoughts about it, but I don't have an answer. I just think it's something that, as a science of intelligence or of embodied intelligence, we're going to be facing.
Yeah. I mean, it reminds me of Jeff Hinton's comment a moment ago. When you say there are infinite number of models that explain the data, well, we don't yet have one model that can explain the data. So even if they're infinite, we haven't found the one which can explain the data we have yet. We have models which explain little bits of the data. So I'm not too worried about the infinity of models, given none of us have been able to generate one model to explain human motor learning in its entirety. So I still think that's a challenge.
I totally agree, but I mean, we're trying to make progress, as you said earlier, right? By defining smaller problems, by pushing aside everything else, and by kind of piecing this together one step at a time, and each of these steps still depends on our ability to do what I said, right? I'm not talking about all data and all of behavior. Yeah. Anyway, I mean, it's something that keeps me awake at night. Because
I just want to. I'm sorry.
I mean, the interesting thing in the human motor control field is how many amazing models are out there which can explain huge amounts of data, and I think are fundamentally wrong. So, there's a very famous model called the minimum jerk model, and I might offend someone here who works at it, which said trajectories are, minimize the rate of change of acceleration squared. And that model has been lots of data, but I just think it's a fundamentally wrong model. And similarly, the dual rate explains lots of data. And it's quite interesting, the history is you can now understand why it explained those data, because it was an approximation to another model, which was more normative or more sensible. So it's interesting how we can fool ourselves for decades by following the wrong model, which explains all the data. I agree with that.
This happens in many areas of science, right? I mean, I talk to vision psychologists who have completely opposing views for decades, and both views are based on data, and somehow it cannot be reconciled yet. And I mean, we're doing behavioral observation studies with cockatoos, where cockatoos live for 50 years, so you cannot have 100 of them because they're going to be there for 50 years. So you have very little data, and you somehow are trying to learn something from these cockatoos, and then you discover that there are so many individual differences to how they generate their behavior that you need to factor out if you want to get at the learning mechanism at all from the observations, right? And so it's a hugely complicated problem. Anyway, I'm just I don't have an answer. I just have questions.
I just want to ask all the panelists here that there are clearly correct models and wrong models, but at the same time, there's no single correct model. I think there are a family of correct models depending on different time scale, depending on different task or context. Is this the view that we all share, or do you think there's one single model that can explain everything?
I thought all models are wrong.
I heard all models are wrong and some are useful. That's
exactly
what I was taught.
But is this in terms of learning any different from, let's say, physics, astrophysics, any science, when, again, we have limited amount of data, we can't always change the task in our context, and we try and explain it with models, and we keep on iterating until we get closer and closer? Or is there something fundamentally different about learning to, let's say, understanding physics or astrophysics or etc.? Is there something unique in this field, or is it just a general problem that we face as scientists?
Oh, I think it's very unique. In physics, first of all, you just have the laws of physics, right? So the systems that we deal with have to deal with the laws of physics and whatever it is on top, right? Some people call it consciousness. I mean, I don't want to get into esoteric discussions, right? But there's something on top of physics that that we do, that we have, that governs our behavior. And that behavior also is much more complicated. I mean, a brick is a brick until you use it for something. But humans, animals, plants move, behave, procreate, and so on. So we have a much more difficult problem and a much harder time getting at data. The behavioral space is much higher dimensional. And I mean, I can have little balls of all kinds of material in my lab forever, and I drop them off towers, and nobody will complain about ethics, right? But if I start dropping birds off towers, people will complain. So it's a very, very unique and much more complicated problem.
Well, and those birds have memories, whereas the balls don't
exactly.
really have so much mechanical memory.
Exactly.
I agree with what you said.
Yeah. So I think we're confronting one of the biggest completely open challenges in science. I mean, we know something about everything. We know about black holes, about red dwarfs, and so on. We found the God particle out. But we don't really know what it is that enabled us to learn about all of these things. We don't know what it is that's that is intelligence. We don't know it at all. And this morning we were discussing what is embodied intelligence, right? We have the second year conference on a topic that we don't know what it is. I mean, yeah.
But we have excellence clusters and institutes and lots of smart people
working on it.
Yeah. I'm not sure there's much else we could do at the point other than be humble and try to learn from each other and take inspiration.
Yeah, absolutely. And it's fun to do that, right? I mean, we're doing it and enjoying it. Absolutely.
And it's an interesting balance of these big questions. And also we are making progress at the kind of the fundamental level of, okay, we see new capabilities, maybe slowly, not as fast as we want, but it's a balance of these big questions, and also at the same time we can make some maybe less significant but developments and contributions, which is nice. Yes. Brilliant. I wonder if any of the panelists, we have, I think, some more questions. Yes, I think, yes, if there's any final questions, please do to raise your hand or put something in the chat. I'm sorry, I apologize, I'm struggling. It's quite a long question, so I'm struggling to pass it in a reasonable amount of time. But if you do have any questions, please do raise your hand and we can ask. If not, I just wonder if the participants, panel members, have any last comments or last thoughts they would like to make as we go into the end of the first day. Famir, I don't know, you started off the day with some points on what we'd hope to discuss and achieve. What do you think we've made? What's the kind of the key takeaway messages you think we've got from today?
I think we have a lot of talks related to neuroscience, brain science, and learning related problems. And I think that was a really good start of really rethink about what the intelligence is, what the embodied intelligence is. I think we're clearly moving forward from the way we thought of in the classical AI type approaches, and we know. Actually, there are lots of things we don't know. I think this is the driving force of this community, and that's why we come here together to discuss what embodied intelligence is. With all these examples of Kenji, Doya, and Catherine, and Daniel, and all other panels and the breakout session discussions, I think we're just trying to make what we know, what we don't know, and that's going to be the really the fertile basis of discussion, I suppose. So, yeah, I think that's my take on for today, and we continue from the breakout session afterwards today, and also the tomorrow and the day after. So, yeah, that's all from me.
My only other message would be to thank Josie for her good moderation and question answering and summary this afternoon.
Thank you. That's very kind.
And both Josie and Famir for organizing the whole thing.
Yes, absolutely.
Yes, yes, and thank you to Arsene and Raymond and Veronica behind the scenes as well. But yes, thank you so much to all the speakers we've had today, to Daniel, Catherine, Oliver, Famir, Mike, and all the many others that have already contributed. And we'll start the breakout rooms in a second. So again, we've got another 2 rooms full of very interesting and exciting talks. So please do stay around and enjoy those. The final message is we will be posting the recordings of today's talks very shortly, and we'll send around an email or a message on Discord as soon as those are available. And then just a reminder, we start again tomorrow at 8:45, and we have another 3 plenary talks and another 2 sessions of panel discussions and short talks. So thank you very much for joining us today, and please enjoy the breakout rooms, and we'll see you hopefully again tomorrow. Thank you very much and have a good evening.